Alright, welcome back everyone. We are going to talk a little bit about lab number 2. I'm going to walk you through the whole process. This one can seem overwhelming and complicated, so I'm trying to make it as easy as possible. If you haven't yet, where you should start is watching the tensile testing video for this week, right? As a review of that video, actually a review of the previous week, we did talk about stress is force over area. And what that means is if I'm pulling on, I'm putting an item in tension, then I have that force is evenly distributed across that cross-sectional area, and it gives us this idea of stress. Stress is really what determines how strong something is, right? We also have this concept of strain, which is change in length, how much it gets longer with that tensile force. Change in length over the original length is this concept called strain. We can use these testing machines, that's what we're going to talk about today, and from that testing machine, if we have something like steel, we can produce a graph where we have our stress on our vertical axis, our strain on our horizontal axis, and I can see the profile. Now this is very important because when we are designing with the material, or want to know how strong a material it is, we need to know what this yield point is. How much force can it handle before it just starts permanently deforming and stretching, right? Then we have this yielded section, and we have this ultimate, how strong can it be before it actually breaks, you know, also very important. And then the at failure, what was the stress? So those are some important points. We talked about the elastic region where this is linear, the yielding, strain hardening, necking. What we're going to try and do is reproduce this graph in this lab today. Oh, another important one, the slope of this line is called the Young's modulus, or modulus of elasticity. It's stress over strain, and that's really important because that is how much force we put on an object. Depending on the material, we can figure out how much it'll change in length, right? So for this lab, what you want to do is you want to go to the modules. All right, so within Canvas, we're going to go down to week 3, Tensile Testing Lab number 2. And I'll see there's some various links in here. The first link says the lab report template. So let's start by taking a look at what this thing is. So if I open it up, what I see is a title, Con 251 Materials and Processing, lab number, lab title, submitted by your name. So basically this is a template, meaning what I would do if I were you is download this to your computer and then start filling in the pertinent information, right? This is lab number 2, Tensile Test Lab, I think is what it was called, right? Submitted by, put your name in there, put mine in there, put your group name and number in here, and whatever day you actually wrote this thing up. Then you have some series of sections. You have an introduction section where you state the goals of the lab, materials tested, apparatus, and how the experiment was performed. We're going to need a data section. What's the original cross-section and width, a table of the data. Should have columns for load, displacement, stress, strain. I recommend using Excel. Analysis and discussion. Now we need a stress strain graph. It needs to have scatter plot, this kind of stuff. From that graph, could you find this yield stress, ultimate stress, failure stress, the strain, and that slope, or the modulus elasticity, those same concepts we just talked about, right? So this is everything we're going to have in this analysis section. In the last section, the conclusions. Is it what you expected? Was there anything weird? Does the graph look like what it did in the notes? What would you do differently, right? Now I'm also including a sample report. So this does have the Lab 2 tensile testing. If you need a little more guidance on what this thing would look like, what about this introduction? Remember what it was supposed to include? Well, I would start off with like, this lab used the universal testing machine with a steel specimen. Specimen is loaded into the machine, and then blah, 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 right? What are the goals? Well, I mean, you can figure this part out. I'm leaving it up to you, but goals would be to determine the ultimate strength, determine the modulus elasticity, you know, all those things that we're looking for. What about data? Well, this is what you'll have your own data table. We'll talk about how to make that in just a little bit, but you'll have width, depth, area, gauge length, all that kind of stuff. You can create your data table. And then in the analysis part, this is what your graph will end up looking like, something like this, right? And then what did you find out for your yield stress? Remember, that's right where this vertical parts are, where this linear part stops, right? What about the ultimate stress? We said that's that highest point there. The failure stress, what's the last point? Strain at peak load. So this is the peak load. What was my strain? I can see it right there. It was 0.0554, right, for this sample data. This is not the data you should be using. This is a sample. Modulus elasticity, how did I find that? That's the slope. I picked a point in the linear region and then divided the stress by the strain, which is our equation. So I picked a point in here. I don't remember which one. Probably like this one, maybe. Yep, 75, 117. Yeah, that's it. So I just picked a point in here. I should get about the same slope no matter which point I pick. This is totally up to you on how you want to interpret your data. And then conclusions I'll leave up to you as well, right? So let's talk about how to create this data table. Going back to our module with Lab 2 tensile testing, the other thing that I see in here, other than the template, the sample, is this data collection tab, right? If I click on that, it'll bring me to a video, a Echo 360 video of me actually performing the lab. This is where your data is going to come from. Now here's what I recommend you do. I recommend you open an Excel document. We don't need to see lab groups. We need a new blank document. There we go. And on this document is where you're going to create your graph, your data tables, and everything else. If you haven't used Excel, this will be a great introductory course. It's not very difficult for what we're going to do with it. I'll walk you through everything, right? But I can already tell you what we're going to be doing is collecting some fundamental information, and it'll tell you this in this video we're about to watch. But if you have an Excel, open up, pause the video, open up an Excel new document, and you're going to want to know the width of your sample, the depth of your sample, and the length. That's that initial length of your sample, right? What we're going to be recording is the load and the displacement. So that's probably all you need to start with, right? Now what I'm doing is I just wrote out these in a cell, and then on this side I'm going to put in those values. So I'm going to get these from that video. So let's start the video, see what it looks like. Alright, welcome everyone. This is the Tensile Testing Lab. In particular, this is going to be a mild steel specimen that we're going to be graphing and looking at the stress-strain profile. Our test specimen looks a little bit like this guy here. You can see it's pretty thin. It does have that dog bone shape where I know all of the strain's going to happen in between these two thicker areas. The first step that we need to do is determine the cross-sectional area that will be supporting the stress. So I'm going to be using our digital calipers and measure that out. So for the width of this specimen, I end up with something like, oh dear, 0.472. So hopefully you can see that, 0.4. So I'm pausing the video, going back to my Excel sheet, and I know that I have a width of 0.472. Enter that into your spreadsheet. Do the same thing for the depth and the length. 0.72. And for the depth of this thing, I guess that's what I would call it, I end up with 0.069. 0.069. So from those two numbers, you multiply them together, that'll give you the cross-sectional width, right? Which is important because we need to know the stress, which is the load divided by area. And you can see over here, what we're going to be looking at is our load and our displacement. So, all right, so like the video said, what we care about is a cross-sectional area. I think I misspoke for a little bit there. So I added another cell called area. You can put these in any order, by the way, just the way I'm doing it. Now the way Excel works is the area is the width times the depth. I need to multiply those two together, right? Instead of actually breaking out your calculator, you can do it within the program. And And the way you do an equation, you're going to say that this cell, this little highlighted bit, is equal to, and then you click on the top one, your little times button, which is that asterisk looking thing, right? And then times that one, hit return. Now I have a cross-sectional area. And it also said the length was 3 inches. If it didn't say that, it's going to say that in a little bit, right? You can't put units in here. Like I can't say that this is inches here, because then when it goes to multiply things, it gets a little funky. So just keep the numbers in there. If you want units, you could put them over here. That's in inches. This is in inches. This is in inches squared. This is in inches. But that part's basically totally optional, right? All right, so let's go on with the video. So the first step is to put this thing into our little chucks here. Here. That's close enough. I'm going to put a slight load on here because there's like let's zero it from here and zero it from here. So what I'm doing is it's there was a little deformed and everything. I'm hoping to take that little deformity out of there, and we can start our test now. So the way this is going to work is I'm going to hit start. We're going to start the test, and then I'm going to hit stop. And every time I hit stop, what you're going to be recording is your load and your displacement. From that load and displacement, then you can calculate your stress, which is load divided by that area we just figured out, and our displacement. Well, actually, you can calculate your strain, which is the displacement divided by your original length, which I forgot to measure, right? So if I put the calipers on here, I don't know if I can still do it in here. I can already tell you that the initial length is 3 inches. So the original length, the distance between that thinner section is going to be under strain, is 3 inches. So let's go ahead and get started. And I'm going to hit start. So I'd record a load of 277, a displacement of 0.033. All right, so at this point, you can pause the video, go back here, and it said a load of 277 and a displacement of 0.033. And that's basically, we're just going to continue this process. I'm actually going to just make this screen smaller so that I can watch it and record it at the same time. I don't know how you want to do it on your end. We got a lot going on here, don't we? But you can see how I'm just going to record a load of like 740, a displacement of 0.064. A load of, we'll call it 1180, displacement of 0.086. A load of 1220, displacement of 0.113. A load of 1280, displacement of 0.151. Displacement of like 1360, load 1360, displacement of 0.192. Load of 1400, displacement of 0.222. Load of 1420, displacement of 0.26. Load of like 1440, displacement 0.298. A load of like 1450, displacement of 0.353. Load of like 1460, displacement 0.391. Load of like 1450, displacement 0.439. Load of like 1450, displacement 0.472. Load of like 1450, displacement 0.509. Load of 1450, 1430-ish, 1435 maybe, displacement 0.547. A load of like 1430, displacement 0.582. Load of like 1250, displacement 0.657. Getting close to failure, I think. It looks like it's, oh, there it goes. So let me stop the test. And what we see is it broke where we'd expect it to, in that thinner section. I can see that's my final shape. Now I couldn't find the final length of this, just for your own information. We started off at a 3-inch length with that gauge length. And right now we're at like 3.576. So yeah, so that's our permanent deformation there, right? So now what you need to do is, I think I have another video, I should have another video on how to do your Excel spreadsheet to find those stresses and strains and do your graph. That's it for the data section. Let me know if you have any questions or comments. Thank you. So this, of course, is that other video, and I am decided to put it all in one video to make it a little easier. Don't know if it makes it any less confusing or not. So here's all the data we just collected for load and displacement. Now what we're looking for is a stress-strain diagram. So I need to calculate my stress and my strain. And just because Excel's a little finicky, it's actually a little easier to do strain first. We said strain is the change in length over the initial length. Well, that's equal. So once again, we have that little equal sign to make this an equation. And I'm going to take the change in length, which is the displacement, and I'm going to divide by the original length, that 3. Now here's a cool thing about Excel. If I want to, I can highlight this by clicking on it, and then see how this little cursor is a white plus sign, and up here it turns into a black one. When it turns into a black one, it means I can click and drag that box down. And what that is saying is I'm just going to copy that same equation all the way down and repeat it. Now if I see I got some weird stuff going on here, the reason being is when it copies it down, basically it's always saying, so the first one were those two, right? If I go down one, this 3 is no longer 3, it's just an empty cell. And this, it keeps going down, but I want it to stay 3 the whole time, right? So instead, the way I can make something constant, meaning it always goes to this 3, is I can put a little dollar sign in front of the C and in front of the 5. And basically what that says is always use column C, always use row 5 in this equation. Now once again, I'm going to copy it down, and now I have this strain for each one of those. As an option, if you thought that was really confusing, you could just say divided by, just type in 3 instead of this C5, right? That'd be another option. We also have to find the stress. How do we measure stress? Stress, we said, is the force over the area, so we're going to do equals to make an equation. We have a load, and we're going to divide by the cross-sectional area. Now once again, what I'm going to do is I'm going to make this C4, the area, to be constant. I don't want it to move. So I have $C, $4, and then I can copy that equation down, and I have my stresses. Finally, I'm ready to actually develop the graph. By the way, this is the table, so I could even stop here and copy and paste this table into my document, but let's go ahead and just do the graph first. The way I do a graph is I highlight my stress and my strain. You can either keep the labels in or not. And then I'm going to come up here to insert. And what I want to insert is an XY scatter plot. This is the plot that'll show the best, not the one that says it's a line. Instead, we want the scatter. Trust me, it'll make your life easier. Now this little pull down, there are multiple types. I would say one of these with the lines, either the straight lines or the more squiggly lines. I'll do straight lines, what the heck. And there I have a graph. Now it needs a little bit of fine tuning because all it says is stress up here, nothing over here, nothing over here. And if you remember that template said we have to have a title and all that kind of stuff, right? So I can just click here, change this title to, let's call it stress strain graph. You could put mild steel, something like that, right? Now, if I look over here, there are no axes, right? So I need to label this. This is my strain, this is my stress, but I need to put that in there. So I can hit this little plus button and say I want to add axis titles, and I see that they've popped up. That's the easiest way to do it. I know if you're doing this on a Mac, I think it's a little different. You might have to do something. I think if you click on this, there was something, chart design, that's where it is. So there's something in chart design, add chart element, then you can add your axis titles. So it's one extra step. I think some programs may make you do that if you don't have it right there. But once they're showing up, now I can label these. So on the horizontal, we're calling this the strain. The units of strain were inches per inch. And on the vertical axis, we're going to call this our stress. And in this case, we have load was in pounds. Cross-sectional area is inches squared, so we end up with pounds per square inch, or PSI. So now I have a full-on stress strain graph, right? So if I go back over to the template that I started with here, and I would actually just use this one, the one that said sample. I would save that as your own, and that way it's a little less work, right? I don't know, maybe not. But you can enter the front page. I think you're fine. Introduction, I'll let you deal with that, and goals. But then we have this data, right? This is where I need to replace this whole data section with my data. So I'm going to delete all of that. To enable editing first. So if you downloaded it, you may have to do the same. And now I want to insert my own data table. So I'm going to go back to my Excel sheet. I'm going to highlight the width, depth, area, length, all of that. And I'm going to say Control-C for copy that. And go into my Word document, Control-V. Now I have a data table. It looks a little ugly because it doesn't have those lines. I could probably make it look a little better by adding those. But I wouldn't take off for that, right? So now you have your width, depth, area, length, your load, displacement, stress, and strain. That's your data that you're working with. For the analysis, it says what we're trying to find is let me move this down so it's on one page. We're trying to find out what the graph looks like. Like I said, this is not, that's the sample one, so I need to replace it with my own data. My own data look like this. So I'm going to hit Control Copy again, paste it into this Word document like that. Now I have a stress strain curve. From that curve or the graph, now I have to enter the information like the yield stress. I have to enter the ultimate. I have to enter the failure. And I have to enter strain at the peak. And last but not least, this modulus of elasticity. So, and I would get rid of this part because clearly that was just for me telling you how to do it. I'm going to leave this up to you. It shouldn't be too difficult. The one thing I'd say is the yield stress. Well, this is all straight line until I get to right there, right? What's the stress right there? 36,231, yeah, so 36,231 PSI. I've told you too much already. What about the ultimate? That's just the highest number. That failure is over here. Strain at the peak, well, you go to that same peak one, the highest value. What was your strain there? Modulus elasticity, you're going to use one of these points and figure out, or both somehow, to figure out what your slope is. I'm going to leave that part up to you. I'm also going to leave the conclusions up to you. Is that what you expected? Does it look like the, I don't know, does it look like the graph that we had in our notes? And if you were to do it again, what would you do differently? Clearly, you'd be in person. That's ideally, I guess everyone can just write that, right? So that's what I got. Good luck. Let me know if you have any questions or comments. This is kind of a complicated one. Hopefully, me walking you through the whole thing here helped out. And good luck. Let me know if you have anything. Thanks.